Hey, hello there. So welcome to the SystemVerilog class session. The classes are one of the very important constructs that have been introduced in the SystemVerilog. And in this session, we will look at it and we will understand this construct and what are the syntax, semantics, and various use cases. Okay, this is the agenda for today's session. We'll start off with introduction. Then we'll look at how so in the introduction, we'll try to understand what is class, how it is defined, and then how do we declare the handles for a particular class, and then how do we create objects for those handles to hold, and then how does a class assignment works, which is slightly different from your regular variable assignment. So we'll look at that. Then inheritance, how do we do the functional reuse? That's what we'll understand with inheritance. Then we'll look at data hiding and encapsulation concepts. How when we do the functional reuse, we want a certain functionality to remain hidden or certain properties to remain hidden. How do we accomplish it? Then there is a group of virtual methods, abstract class and polymorphism. So these virtual methods and abstract class together helps us realize the polymorphism, which is basically your interface reuse. And then we will look at parameterized classes, that when we have like certain variables, widths or data types, those can be parameterized, very similar to the parameterized modules. The classes can also be parameterized. We will look at it, and then we'll look at an interface class concept. So interface class concept is not, this interface is not our SystemVerilog signal interface that we have seen. There's a separate overloaded term. I mean, the interface is an overloaded term. Interface class is a different concept wherein we are spreading out a common functionality that needs to be implemented in one class across multiple classes, because it is a part of one class but needs to be implemented by different components. So how do you accomplish that? We'll look at it in the interface class, and then briefly we will look at memory management, that how does the storage space gets allocated for the data present in the class and how it gets deallocated. So we'll look into that. Okay, so before we jump deep into the class construct and its usage and all that, let's ask ourselves a question: why do we need object-oriented programming? Okay, so this is the typical question that we ask, and then we can give all type of general answers that we are going to give, and we are going to look at it anyway as a part of this session. That it will be abstraction, it will be inheritance, it will be polymorphism, but we are asking a wrong question when we say why do we need object-oriented programming, right? So the real question that we need to ask is, what is a good software design? Because that is our intent, whether it is object-oriented programming, procedural programming, declarative programming, or some other programming paradigm. Ultimately, what we are interested in, or why do we explore new programming paradigms, is that we want to do a good software design. That is what we are really interested in. And then if we ask what is really a good software design, a good software design is something that it not only meets its primary functional requirements, but it eases the enhancement and maintenance. Okay, unlike we creating some structural, let's say a building, right, which we plan once and build it and then forget it for years together. Software is mostly a living entity that undergoes a constant change in one or other form. The bug fixes happen, the enhancements happen, and it keeps shifting hands. So from one person to another person. So the ease of enhancement and maintenance is a very key component for a success of a software. And that is why a good software design should be able to ease this enhancement and maintenance. And in order to do that, we need a property called a high cohesion and low coupling. Okay, these two are very important. We will look into it as to what they are. And the object-oriented programming, it generally promotes this two characteristics, that it makes the program to have a high cohesiveness and low coupling compared to procedural programming. Okay, and because of that, we want to use the object-oriented programming. Now let's understand this cohesion and coupling. Although the terms themselves sound like a big deal, but there's no big deal in it. So if you remember, like even our simple FIFO test bench, uh, let's take a concept that we had a generator and we had the driver. Okay, so let's say this is a generator and this is the driver. Now, what we want, what do we mean by cohesion is that a generator should contain all things, all the functionalities, all the responsibilities, all the behaviors that it needs to do the stimulus generation, right? That its functionality should not be distributed in the driver. Okay, all the related functionalities, they have to be cohesive, right? They need to be together, they stick together closely. All the related things should stick closely at one place, right? So if I'm looking at a math library, I should be able to find all math related functions. If I'm looking at a geometrical library, I should be able to get functions to draw various shapes. It should not happen that one type of functionality is in another type. It becomes confusing, okay, and you cannot build it more optimally. So all related things should stay together more closely. That is the cohesiveness. And then when one type of a functionality, one major type of a functionality interacts with another, that is, I am doing transaction generation in generator and I'm passing for execution to the driver, the way we communicate from generator to and driver should have a low coupling. Low coupling meaning I should be able to easily disconnect them and take them apart and take this generator and put it with another type of a driver, or take this driver and put it with another type of generator, right? So they should not get so coupled that the generator starts calling the functionality of this specific driver and the driver calls functionality of that specific generator. Now they are tied together, right? So we cannot isolate them together, in which case the reuse becomes limited, because I can't take this driver and put it somewhere else, or I can't take this generator and put it somewhere else, right? So cohesion means related functionality should be together closely, and the coupling means that how they interact with each other. Okay, so low cohesion, the high cohesion means they should be tightly coupled, related things should be tightly coupled, and coupling means whenever you interact with other modules to get the job done, the interface with which you interact should be easily we should be able to easily break it and put it with another thing, right? So that is the idea of high cohesion and low coupling. Okay, so the next question is, how does like object-oriented programming really promotes high cohesion and low coupling, right? That's the next question that we will get in our mind. And in order to answer that, let's contrast the object-oriented programming and the procedural programming from the point of view of cohesion and coupling. Okay, so in the object-oriented programming, as most of you might have at least heard of it and seen some parts of it, I'm sure. We encapsulate the data and the operations or the subroutines together into classes. Okay. Now, when you do this, that becomes a self-contained unit, right? And so now what happens? The data and the methods that operate on data are coupled tightly together. Okay, so that is what is happening in case of the object-oriented programming. But whereas when you look at the procedural programming, right, both the data and the functions, they are kind of loosely organized. When you look at a C program, you have declared some data, you have declared some functions, and there is no clear-cut division as to which function is going to modify which data. That is not defined, right? And it's very separate. There is no sense of relationship between them, and this lowers the cohesion, okay, because we don't know, and their related parts could get scattered in different parts of the program, and there is no way to prevent that, or there's no way to promote a construct where we can put them together. So that's why procedural programming results in low cohesion, whereas the object-oriented program results in the high cohesion. Now, if you look at from the coupling point of view, so what happens is when we look deeper into the class constructs capabilities, we will see that both the properties are nothing but your data, and the methods, which are nothing but your subroutines, right, is just another term. We can have different qualifiers, like we can say it is a local, then it's a protected, or it's a public. Like that, what we can do is we can do the access control to the properties, and we can always say that when one class interacts with another class, it cannot call a local method. Okay, it has to call a public method. So when we impose such access restrictions, the interface through which one module can interact with another module becomes very well defined. And because of this, what happens is that this class cannot know too much of in detail working of another class with which it is interacting. It has to only interact with few set of functionality, so it doesn't know, oh, it's implementing internally a counter which is modifying, then setting some other flag and then returning me this information. That type of process gets hidden from the another class which is trying to use the functionality of this another class, right? So now there is a less coupling between them, and the less coupling is not only important that I can pluck out this component and reuse it somewhere else, but it's also important from the point of view that if I do some changes in one component, it should not have an inadvertent or the adverse effects on another component's functionality, right? So that is it is another benefit that you get out of low coupling. But when you look at the procedural programming, you generally have lot of shared data, and then any function can come in and modify any data. And even when I have put in certain set of functions, if I want to identify that okay, these are the set of functions that I really want somebody to use, there is no way I can kind of impose that particular rule, right? Anybody, once they are able to see the function declaration or the shared global data, there is nothing to prevent the usage or to restrict the usage. There is nothing, there is no mechanism, so in which ends up that anybody can use anything, anybody can call any function, and this leads to more unintended dependencies on each other, because they get all strongly coupled, and such a highly coupled system that I change something, it affects everybody, and they become more fragile and error prone. So that is where the procedural programming has the low coupling. So these are the two key important concepts that you need to understand, that the high cohesion and low coupling is what makes the object oriented programming more useful. Okay, so let's contrast the class with module. So we have seen module in Verilog. So unlike module, class gets created dynamically, okay, and it also gets destroyed. If you compare a module, once you create a module, it gets created at the time when the simulation begins, and it doesn't get destroyed till the simulation ends. Unlike to the module, class can be created during the course of simulation. That is, simulation has progressed to certain time at 50 ns or 100 ns or whatever, some 500 ns, and you can create a class at that point of time, and then we use that class, and then it could get destroyed at, let's say, 5000 ns, whereas the simulation might be ending at 10,000 ns. Okay, so you can dynamically create and destroy the class, and because of its dynamic nature, you cannot compile a class standalone. That is, I can write a hello world module, but if I write a hello world class, then that class has to be put into a module or any of the standalone constructs like a interface or a package to be able to compile it. It cannot be compiled independently and simulated. And as we looked at it, why the object oriented programming is important, and this object oriented programming is made possible through the class construct in SystemVerilog, right? And the object oriented programming, predominantly the main purpose of the object oriented programming is to enable the reuse and reduce the effort in enhancement and maintenance. And this is exactly the reason why, if you look at the verification methodologies, most of the verification methodologies, we are going to see many like the evolution of in the evolution of verification methodologies, all of them have started once the SystemVerilog has come into existence, not when the Verilog was there, right? Like be it VMM, OVM, and then now today UVM. So all of them are built on the top of SystemVerilog because they are reusable framework, right? They're a framework for the reuse, and that's only possible because the SystemVerilog provides this construct called class, which makes the object-oriented programming possible. And the object-oriented programming promotes the reuse, as we saw at a high level, through the high cohesion and low coupling. But the low level concepts that get utilized are like the abstraction. So abstraction meaning that you build a particular component, and the user of that particular component need not know internally how it functions. He uses it only through a set of interface functions that have been provided, and he doesn't have to worry about how it's internally operating. And that's possible with the help of grouping the data and methods together in one entity, and then being able to do the hiding, right? That is, you are able to control the access control to the external module as to what properties are accessible, what methods are accessible through help of the qualifiers that we will look into more details. So we have local, protected, and public type of qualifiers. Through those qualifiers you can control the data access, and that is what is the abstraction. So encapsulation, you are putting the data and methods together, and through the qualifiers you are able to control the access to those properties and methods to the external world. So it can only see it through the windows of properties and methods that you have enabled it to see, and the rest of it remains hidden. So that is the abstraction. And then there is this concept of inheritance. So once you have built this nice component, then what you can do is you can either build the extended functionality of this particular component that you have created, that is the inheritance, or you can do the polymorphism. So polymorphism is essentially a reuse of an interface. Interface here doesn't mean the signal interface. So interface meaning like the set of functions that we want to call. That is the interface that we are talking about. So there can be some interfaces which are very powerful, and they can be reused through the concept of polymorphism. Okay, so we will see the examples. At that point it will become clear, more clear. So through these concepts, object-oriented programming enables the reuse. So this is the overall scope for learning the class. So like for someone to say that I have understood what the class means, he or she is supposed to know like the class construct, the properties, the methods, and then the notion of handle, object. So this distinction is very important. When we go further, you will be able to see what's the difference between handle and object. What's the constructor? We have seen it to some extent of all these concepts, but we will now more formally define it and go slightly deeper into each of these aspects. Then how the assignment between the class handle works. Then there is a concept of copy. We will look at it. There is a deep copy, shallow copy, we will understand. And then how the static type of properties work in the context of class. And then when we say data hiding and encapsulation is just a high level term. When we translate it into low level qualifier, what exactly does it mean and how do we implement it? And then there are various forms of reuse. We can do composition, in which you are essentially instancing one class inside another class. That's your composition. Inheritance, you are extending one class and adding more functionality to it. And the polymorphism, where you have just defined the interface, you have not defined the functionality in a base class, and then you extend that to define the functionality, and multiple guys extend the same interface to define the functionality. That is the polymorphism. And then we have the parameterized classes. So this is the slightly advanced topic. Parameterized classes are they are used in building the UVM library as well. And then we have interface classes, which is a very super advanced concept. So we will still briefly touch upon it. Will not go into the all the details of interface classes. We'll just see. So interface classes are predominantly used in building the library. So but we will just look at what is the concept. So this is the overall scope of what it means to learn a class construct. Okay, so let's jump into a class example. I mean, class is nothing new. We have already seen various classes in our FIFO test bench. and this is one of the class from the FIFO test bench itself, which is a FIFO config. So let's look at what are the various components that are present in the class. So first, through the pre-processing macros, you generally provide the multiple inclusion protection. So it checks if not defined a particular macro. This macro name, generally you want to give the name of your class itself. You can add some prefix, and then you say tick define this particular same name that you are checking. So the way it works is that since first time when the inclusion happens with a tick include, this macro wouldn't be defined, and once it gets included, this macro gets defined. So if we do multiple inclusion somewhere accidentally, then this macro will prevent the multiple definition error. Okay, so that's what is this protection for. So it's generally a good practice to do that. Then you use the class keyword, you give the name of class. Okay, that's the first thing that you do. And here we are, whenever we do this class, it's actually a data type. We are creating a new data type. So here we have created a new data type called FIFO config. So when you declare a class, the way it behaves is going to behave like a data type. So because eventually we'll see when we declare a handle, then this name we are going to use it on the left hand side, like the way I say int and the name of a particular variable, right? So int is a data type. So any class name also is used on the LHS side, and then space, and you define a name on after the space, right? So I'm talking about LHS and RHS with respect to the space between the name of the data type and the name of the variable, right? So with respect to that space, the left hand side is a data type name, and the right hand side of that particular space is the actual variable name. So same concept is utilized even for the class. We will see when we declare the handle. So here we are creating a new data type called class. So class FIFO config, and then next comes all the properties of the class. So these variables can be class data type as well. So that's what creates the class composition. So we have already seen, for example, in some of the classes we had created instance of, like a generator, for instance, had a instance of FIFO config and the FIFO state, right? So it had the instances of those. Okay, so you can declare, so any data type can be declared over here, and you can as well declare another class itself as a property, and you can add this additional qualifier rand. We will see more about it in the session on constraints. So we have already seen how the overall usage in the FIFO test bench for randomization. Then you can add constraints and the functional coverage of this particular properties over here in the class. So for the whatever the properties that you have declared, you can add the constraints and the functional coverage for it. And then there is this function new that you need to define, which gets called whenever the object of this particular class type gets created. Okay, and this function new is used for initialization, and it does not have any return type. If you see, it's just function new, it's not function int new, so it doesn't have any return type. And you are expected to create an explicit constructor when you have some initialization of the properties of the class, right? So if you want, whenever this particular class objects are created, if you want the properties of this particular class instance to be initialized with a specific initial values, then you can write a constructor, and you can also pass arguments to the constructor, which you pass when you create the object handle. And similar to tasks and functions, you can even define the default argument values. And if you don't declare the explicit constructor, then the implicit constructor gets provided automatically by the SystemVerilog itself. So the implicit constructor will called automatically if there is no explicit constructor. And then towards the end, you can define multiple tasks and functions which will operate on the properties of this particular class. Okay, and then you have the end class keyword, and then we have this tick and if, and this essentially completes the quick decomposition of what is contained within the class. So we have class is a data type, we have declared the properties, and then you can declare any constraints and the functional coverage associated with this class as per your requirement. And then you need to define the constructor. Constructor is a special function that gets called automatically whenever the object of this particular class gets constructed. And then you can define set of tasks and functions which are properties which can operate on the properties of this particular class. Okay, so in the previous slide we saw that the methods of the class, the actual functionality of that particular method was declared within the class. Okay, so there's one way to write the class, and there is another way to write the classes wherein you can use this extern keyword. So this is again another component from the FIFO test bench. I am looking at the push monitor. So you can use the extern keyword, and then once you use the extern keyword, then you don't need to define the actual body of this particular function or task within this class declaration. Okay, so you don't need to define the actual body of this particular task or function. Then what you can do is you can define the functionality of this particular method outside the class. Okay, but this declaration has to be visible to this particular implementation that you are providing. So now this becomes a prototype. This becomes a prototype of your method, and then the implementation of the prototype you can provide it externally, and this is the syntax you need to use. And the prototype and the implementation must exactly match. That is, function, it should match function. Then you use the scope resolution operator. This 2 double colon is the scope resolution operator. You use that to tell that this particular function belongs to this class declaration, and then you provide the name of that particular function, and these arguments that have been defined, they have to be exactly matching in terms of the number of arguments, their position, the type, everything should exactly match to the prototype that you have declared within the class declaration. And then you can define the functionality. Then it's a regular end function that you can do. Now, one benefit of doing it this way is that if you have a very big and complex functional class, then when you open the class, you just want to get a quick glimpse of what are the properties and methods that are present. You don't want to jump into the details of what exactly a particular function is doing. So you just want to get a glimpse of, okay, so this is the push monitor, this has a constructor, and this seems to have these 3 tasks, push, interface, monitor, main, and run. Now when I look at this, it gives me a quick sense. Oh, okay, so run might be calling the main, and then main is calling this particular push interface monitor, and that's where I'm implementing my functionality. So I get a quick big picture when you declare the methods with the extern. For small classes it doesn't matter, but if you have a big and complex classes where the functionality of each function spans at least, let's say, 2-page worth, or like even more than 1 page, and then you have at least like about 8+ methods that are present within the class, then if you put everything together in that class declaration, it becomes hard to absorb all the details. So you can use the extern keyword and provide the implementation to the prototype outside, so that getting the big picture becomes easier. Okay, so in the previous slide we have seen the definition of the class, and that's like a blueprint. Okay, so plan. Now we need to implement the objects of that particular blueprint. How do we do it? Let's look at it. So I have taken the code snippet from the FIFO test bench, and this is the push generator. So I've just taken a relevant piece of the code. It's not a complete code. So here we have declared a FIFO transaction handle. Okay, so as we had talked about, the a class is a data type. So we are saying we have created a FIFO transaction which is a variable of the type FIFO transaction. So that's that class handle or class variable. That's what we call for the FIFO transaction. And then the default value of this particular variable, right? So in the data type section we had seen that every variable that we declare has a default value type. So the default value type for a class handle is null. Null is the special value, so it will contain null. And then in many cases, when the class handles are passed to either functions or even sometimes within the constraints we refer to class handles, we can check whether the class contains, the handle contains a legal object by checking for this value equal to null. So you can say if a FIFO transaction equal to null, this tells whether the handle that you are accessing is pointing to a valid object or not. You can check that by doing this equality check to the value null. Okay. Now, if you look closely, so we'll come to this last point. Let's hold on to it. So the next step that we are doing over here is we are saying this FIFO transaction equal to new. Okay. So when we do this, we actually allocate an object of the type FIFO transaction. Okay. And that object will be pointed by this handle FIFO-tr. Okay. And when we do this, the new constructor that we had defined within this particular class gets called, and that constructor will do the initialization of the different properties if whatever we have done will take place. And if the explicit constructor is not defined, then the implicit constructor will get called anyway, and the properties of that particular class would be initialized with whatever the default data type based initialization, right? So that's what will take place. And then after we have created an object for a particular class handle, the properties as well as methods that are present within that particular class can be accessed with this dot notation. So for example, if you see over here, I am saying FIFO transaction dot randomize. So dot randomize is actually a built-in method that is present within every class data type. So I can access that using dot. Similarly, any other properties that are publicly accessible, any other methods that are publicly accessible, I can access them using the dot notation. Okay, so now coming back to this point, so what happens is that I have done a new over here and an object gets allocated, and then I randomize that particular object and I am sending it from generator to push driver through this mailbox. I am sending this particular transaction, and when I do this, what happens is actually the handle or the pointer itself is traversing to the driver. Okay, and then the driver will do and this put, as we know, gets blocked because we have sized each of these mailboxes to 1, if you remember. And then the driver will do the driving functionality. It will do the peak process get loop. So it will do the peak, get this particular handle. So it's getting a handle, okay, not a copy of it. It's really getting, and they are both at that point, both the generator and the driver are pointing to the same object. Okay, that is something that you want to keep it in mind. And then you do the peak, you get the handle, you do the processing, that is you drive the interface, and then you do the get. Okay, and there we do the get, and once we do the get over there, the class in that particular whatever the variable class handle variable that we have is now again continuing to point to the same object. And here this gen2 push driver.put gets unblocked, and when it comes back over here because of this repeat loop, and when we do the new over there, now only the handle present in the driver is still holding reference to this particular object, and because of that this object will still remain. And when the next put happens, right, the peak there will get unblocked, and that peak will now get a new transaction handle, and once it gets a new new object handle, the previous one will get dereferenced, right? So now because now there is nobody pointing to that particular object because the generator has done a new, and then it has sent that handle, and then now the driver who was previously holding that particular handle has also deallocated, dereferenced it because he is now pointing to this new transaction. What happens is that the object at that point gets deallocated. Okay, so this is what it means. So you can actually trigger an explicit deallocation as well, and it's a good recommended practice that if you have bigger objects, once you have used them, it is generally a good practice to assign null to them. So when you assign null to them, and when all the references become null, that particular object gets deallocated. So that's what happens. And I just wanted you guys to think that if we had to do the same thing with a module, how would you go about it, right? So we cannot create dynamic modules like this. We cannot create a loop. We have to create the code statically, and then in the future we will see how the classes can be, functionality can be extended. We cannot extend the functionality using the modules. Okay, and if even if we do instance a different module, submodule within a module to extend its functionality, it still leads to creation of a hierarchy. And when that hierarchy gets created, any functionality I have to refer it through that hierarchy. And if there is some change in that particular hierarchy, then again we need to do the change in the code. But when the class gets extended, even through series of extensions, all the functionality is available within the same class handle. I don't need to refer it hierarchically. You will see that in the future. And then even the static, whatever the allocation that we had done with the module would have retained throughout the duration of simulation, but whereas with the class handles, as we are able to see, it is getting deallocated. Okay, so I am showing one more example, and we will look at the use case for this keyword. So here I have put a code snapshot of FIFO state, and you can look at over here, right? So we have put the constructor, and in the constructor we are initializing the properties of the class. So we are saying this dot pop count equal to 0. So we have used this keyword. So this keyword actually refers to is an implicit handle to the class instance. Okay, so it's an implicit handle of this particular class instance. And because when this method gets executed, it would execute on that particular instance, right? So and when it is executing in the context of that particular instance, that instance is referred with this keyword. And you can utilize this keyword to access here. I am showing only the properties, but you can use this keyword to even access the method. Okay, but what you need to note is that even if I had not used this keyword over here, and instead if I had just set pop count equal to 0, then would it work? Okay, so the answer is yes, it will still work. Now what happens when you don't do that is that it will first look for this pop count variable within the function scope. Okay, if it is not able to find, if your simulator is not able to find it within the function scope, then it will go to your current class scope and try to find it, and then it sees the pop count, and it sees the pop count is declared, and so it's all good. It is going to go and initialize it. And if it was not there in this particular class scope, then it will look at base class. So we will see concept of inheritance when we do the extended from. So it will look at this particular variable in the base class, and then if there could be a multiple levels of inheritance, so I can extend from one class to another class, like base 2 extending base 1, and then base 3 extending base 2, so on and so forth. There could be multiple levels, so it will recursively look through until there are no more base classes, and then it will look at the outside the current class into the package or module, wherever this particular class has been defined. It will look at it over there. So unnecessarily it will do that traversal, so you can minimize that by putting this. I think that's the main use case for this keyword. Okay, so pay attention. This is a important concept that we are going to look at. So when we have multiple handles of a class, and we can now do a different types of assignment. There are 3 types that we can do. We can do a pointer copy, we can do a shallow copy, and we can do a deep copy. Okay, so here what I have done, I have declared 2 handles of FIFO transaction, T1, and then I have declared it as T2. So let's look at what happens in the pointer copy. So I created T1 equal to new. So when I did this new, an object got allocated, and that object is now pointed by this particular handle T1. When I said T2 equal to T1, okay, what happened? Now there is no new object that got created. Okay, this is a very important point. When you set T2 equal to T1, there is no new object that got created. There is a single object. That is, if I had a FIFO transaction and inside that, let's say I had a data variable, there is only one storage that has been allocated, and that same storage will be pointed by both the T1 and T2. So if I modify T2.data, then the same would be even reflected if I access it with the T1.data, because both of them are pointing to the same object. Okay, and then if I then say T1 equal to null, will the object get deallocated? Answer is no, because still T2 is pointing to that particular object, and only when I say T2 also equal to null, right, then what will happen is that particular object will totally get deallocated. So this is the concept of pointer copy. So in the pointer copy, there is a single object and multiple handles are pointing to the same object. Okay, then there is a concept of a shallow copy. So if I want to really make a copy while I do the assignments, how it works. So I am saying T1 equal to new and T2 equal to new of T1. So when I do this, then what happens is the constructor will not be called for the T2. Instead, all the variables that are present within this particular class, which could be of integers, strings, instance of handles, everything just gets copied over from T1 to T2. Okay, it gets copied over. So when you do the shallow copy, there are actually two objects getting created, and the content of the second object are copied from the content of the first object. Now what happens is, let's say we have a gen push, right? So I have declared two objects within this particular class. Okay, so the value of these two handles also gets copied when I do this. Now when that gets copied, those are still pointing to a common object. Okay, T2 and T1 are pointing to different objects, but within that object, if there are any handles, those internal handles still point to the same object. So within T1 and within T2, if I had this state and config objects handles, those handles would be pointing to the same object, whereas T1 and T2 itself are pointing to different objects. So this is a shallow copy. This concept is called shallow copy. Now if you truly wanted two objects and all the internal object handles also to have their own copy, then the way to do it is that you create two objects and then you call T2.copy of T1. In this case, what we need to do is we need to write this custom copy function within this particular class that goes over through that particular class and identifies if there are any class handles. If there are class handles, it again allocates that particular class and calls the copy function of that particular class similar to this way, right? So it will say whatever the FIFO state dot copy and that particular object handle dot FIFO state, right? So that that particular content can be copied over, right? So that recursively it needs to be done with the help of the custom function. So if you want to do the deep copy, there are no built-in mechanisms. This is an important point that you need to notice. Through built-in mechanism, either you can do pointer copy or you can do the shallow copy, but you can't do the deep copy. Deep copy meaning even the objects which are present within that particular class handle, if you want to make a copy of them, then you need to write custom functions and you need to manually do the copy of all the properties that are present within the sub handles of that particular class handle. Okay, so this is how it works for the class. These three concepts work for the class. Okay, let's look at static properties and methods that can be put in the class. So there are two key concepts that you need to remember with respect to the static properties and methods. When you declare any property within the class as a static, okay, then the same property gets used across all instances of class. Okay, this is the important point. So even when I create multiple object instances, all the objects of that particular class for the static will refer to the same storage. That is, we have generally seen whenever we did new, per instance storage got allocated, right? So if I had multiple handles and if I said new to each one of the handle, each of the handles allocated storage for all the properties that are present within the class. But when the property is of the type static, then there is only single copy of that particular property that exists, which gets used across all objects. So this is the first important concept. Okay, and where is this useful? So let's say I have a file that I have opened and I want all objects to write something to the same file. Okay, so I don't want every object to have its own file. So if I create thousands of objects, I don't want to end up with thousands of files that is getting logged from that particular object, right? So I want to have only one file. So I can open one file ID with a static property type and then use the same file ID across all object instances. So this has the static properties do have use cases. And then like let's say I'm creating this packet class, and if I want to keep track of a packet count, then I want to have a unique ID. Okay, so that's useful for me in debugging. So because we can create n number of transactions, right, in the constrained random environment. So I can create one static packet count property within the class that I can keep incrementing and then assigning it to the unique ID, and thereby keep like sort of a unique ID per packet that gets created. Okay, and this packet ID I keep on incrementing. So and hence what I can do is for every instance it automatically gets updated. Okay, so although still it's a property of the same class. So these are some of the use cases for the static properties. Now let's look at what does a static method mean. Okay, so pay attention over here that when you declare a static method, it's like any other method that you are going to declare. The main difference is, this is the main difference, okay, and this leads to these 2 points. Okay, so the main difference is that you can access a static method without really instancing a class. Okay, so I have declared a static method called next ID over here, and what I'm doing, I can now access this particular next ID function. I have not even created any instance of this packet. I can say packet, which is a data type name, then scope resolution operator indicated using this 2 double colon operator, which we had seen even in the case of extern keyword, and then I am calling this particular function. Okay, so this is the static function. So any static function of a class can be called without creating an instance of this particular class. Okay, this concept you will again see it in UVM also. Like for example, UVM config.db, we will be using it as a static class. We won't be actually instancing it. Okay, so this is a very important point, that you can create a class and then you can access the static method without really creating the instance. Now when you don't create any instance, okay, the other non-static properties are not allocated. So that is why you cannot access non-static properties within the static methods. So here we have accessing the packet count, but packet count is again a static type. But like I cannot access a unique ID within the context of the static method, because those properties do not exist, because I'm accessing them even before creating an instance of class. And this handle within the body of a static method is illegal, obviously, again for the same reason, because this refers to an instance of this particular class, and that doesn't exist because we can access directly. It doesn't, again, and the next point is, it doesn't mean that the static method can only be accessed using the scope resolution operator. That is not correct. It can be accessed using scope resolution operator without really creating instance of it. But if you have an instance, like for example here we have an instance of, let's say let's say P1, right? So I have created an instance P1 new. I can access it directly. Okay, and even when the object instance is not created, okay, you can still access the static method. So, okay, that is another funny thing, that not only using the scope resolution operator you can access it, even when the object is not created, you can access the static method. So that is the speciality of the static methods. And then You can actually have automatic variables within the static task as well. So if you want to call a static method in a reentrant way, you can create automatic variables and still be able to use it. So that is still possible as a use case. Okay, we have looked at the basic abstraction and encapsulation, wherein we have packed together the properties and methods and how to implement the methods within the class external, as well as we have looked at some of the static keywords usage. Now we will look at the second important concept in object orientation, which is the inheritance. And as we have been seeing, the object orientation's primary promise is how to improve the reuse. So inheritance actually promotes a functionality reuse. So we will see polymorphism, which will promote an interface reuse. Compared to that, the inheritance promotes the functionality reuse. You have created certain functionality and you want that functionality to become available to a next class. That is what is the key idea of inheritance. So the primary premise is that we have some common functionality, okay, and that is useful for, let's say, multiple components, and we want that common functionality to be available to both of them. So here we have class 1, class 2, we have some common functionality and we want this to be available to both of them. So one very simple way that you can understand inheritance is through this example, that let's say now in the absence of inheritance, let's say if I had only the class construct available, what would I have done? I mean, it's not an exact what do you say, this is not an exact way the inheritance is implemented in the language. This is just to make understanding easier. Okay, so what I would have done is, if I had this common code, I would write it in another file called base.svh. I am not putting any construct, I am just creating a new file, and in that new file I am just putting in this code. I am putting in one variable and one function. I'm just putting it in, and in another class, let's say now this packet class is nothing but a C1. If I want to reuse this code, I will just tick include this particular file that I have created. So as we know, the tick include pre-processing macro will just bring in, it will literally copy paste the content of this file into this file. Now, although I'm showing everything in one single screenshot, imagine this class packet is present in a file called packet.svh, and the base.svh is a different file. So we have two files, and then in the second file I am doing a tick include of base.svh, and when I do that, literally this content is copy pasted over here. Now I can have another class C2 which is in another file. I can do tick include over there. So this way what I am able to accomplish is that I have some common code that I am able to reuse across multiple classes, and that is the concept of inheritance. Okay, so don't take this example too far. This is just to make you guys, just to give you guys the how the concept works. Okay, but the real way it gets implemented in the simulator is quite different. Okay, and we will see it further in our next session, that how do we implement inheritance through the SystemVerilog. In the SystemVerilog, how do we implement? We look at it. And one final point before we move on to looking at how the SystemVerilog does it. So UVM, actually the universal verification methodology sessions that we are going to be doing, it heavily relies on this concept. Okay, the inheritance as well as the polymorphism, it heavily relies on that. In the UVM, what happens is we get certain reusable base class libraries. Okay, so the way we have done this common reusable part that exists in the implementation of testbench is delivered as this base class libraries, and that is what we extend and build our testbench component. So inheritance is very much used. So if you understand these concepts, then while we start doing UVM, things will become slightly simpler. So when we say that we want to make the common code accessible within multiple classes, the question that comes to our mind is, in SystemVerilog, how do we do it? How do we tell a particular class that, okay, here is the code, that's a common code that is present that I want to inherit? How do I tell that? That's the first point that comes into our mind. The second question that comes into our mind is that once I inherit something, how do I access it, right? How do I get inheritance and how do I access my inheritance, right? That's the question many would be asking. So how do we do it in SystemVerilog, right? So we use the extends keyword, which is sort of loosely equivalent of the tick include concept that we talked about. So you say extend. So let's take a look at an example. This is the example that we had seen in our FIFO test bench. So we had a base test, and this concept of base test and having multiple tests is going to continue even in case of UVM or in any way you implement, because all common functionality in the test suite that exists across all tests is always put in a base test, and you extend that base test in different tests to implement unique scenarios in the extended test. So you say class, and I am saying basic push pop test, which is one specific scenario implementation. I am saying it extends with the extends keyword. Extends keyword will say that we are inheriting the contents of base test. So when we say inheriting, what happens? This entire thing that exists within the class base test now becomes a tick included equivalent. It becomes a part of the class basic push pop test. Okay, it becomes a part of it. Now once it becomes a part of this particular class, then you can access the properties which could be like, let's say, this environment or the methods which are like, you know, new and run. All these properties and methods can be accessed as if they are part of this particular class. That's why the analogy of tick include was brought in, because now it is equivalent to this entire content is as if it is present in this class. Okay, so it's equivalent to that. So that is why you can access any of them using this keyword. For example, here you can see this .env.FIFO config. We are able to access the content of this particular base class as if this env class handle is present within this class basic push pop test. Okay, so we can do that. And when the, so that is one aspect of it. So we now know how do we sort of inherit, and we know how do we access the inherited properties or the methods, inherited classes properties or methods. The next important concept is what happens to the constructor. So when the derived class is new, so when I new the when I create an object of the type class basic push pop test, what happens is the automatically the base class constructor would be called. Okay, after the base class constructor execution, you will execute the constructor of the derived class. Now when I say it is already getting called implicitly, but in the example I am calling it explicitly over here, right? I am calling super.new and I am passing this argument env. So why am I doing this? Okay, so that is a question. So why we are doing this is that when the SystemVerilog implicitly inserts a call to the base class constructor, it inserts it without any arguments because it wouldn't know. Okay, so by default its implementation, it would insert a super.new without any arguments. But if you are passing any arguments through the constructor, because constructor, as we have seen, is like any other function which returns nothing, but if you can take arguments, right? So if you are taking arguments in the constructor and you want to pass those arguments to your base class, especially if the base class constructor takes the arguments and you want to pass the values, then you cannot rely on an implicit constructor call. You have to call it explicitly, and typically you want to initialize your base class properties before you initialize your extended class or the derived class property. So you have to if you are passing the any arguments, you need to call super.new explicitly. The other way that you can do is, if either you don't have any arguments in the base class, if you have an argument, then you can provide default values. So if you provide default values and you don't intend to pass the value from the derived class, then also you don't really need to call super.new. You can use the auto insertion. But if that is not a case, you need to pass your base class constructor takes in an argument, and that argument needs to be passed through the extended class, then you need to explicitly call super.new. So that's how the constructor cascading works when you extend a class. Okay, so let's look at take a look at this super keyword. So we used it in the previous slide as well. So super keyword actually refers to base class from its derived subclass. Okay, what does that mean is, I can have any level of inheritance hierarchy. So I could be saying I have a class C1, I have class C2, C2 is extending from C1, then I can have another class C3 that extends C2, I have a C4 that's extending C3, so on and so forth. I can have multiple levels of inheritance that can exist, and at any level, if I say keyword super, I am just moving one level up, only one level up, right? So when I say super keyword at C3 level, I move to C2. If I say super keyword at C4 level, I move to C3, and so on, right? So you can move one level up, and typically we have been seeing that we are using the super keyword to access the constructor. That's a base class constructor in the derived class constructor, but it can be used for the other methods and other methods as well. You can actually access the base class properties, or you can access the base class methods. Now one would say, hey, why do I need to do that? Anyway, when I have extended, everything is accessible through this keyword itself, right? Because it's a part of the same class, then why do I need super? So this is very helpful when you are overriding the method. So here also, if you see, there is a function new which is present even in the base class, and a function new that's present in the derived class. Okay, so that is why when I need to initialize my base class, I need to call super.new. Okay, the same concept applies, that there could be there can be methods within the base class, and even the functionality of those base class methods could be extended. Okay, so in that case, what happens is, you will have in your derived class, you can have new functions and new tasks, and as well you could be overriding an existing function or existing task that's already present in the base class. Okay, when you do that, then what you need to do is that whenever somebody calls a same function or a task from the derived class, you also want to call the functionality that is present in the base class, because you are extending the functionality. Essentially, the way, whatever the concept that we are doing with the constructor, the same concept would be applicable if I have extended a functionality of any other function or a task. So when I call a function from a derived class, and if that is the same function or task also exists in the base class, then I will first call the base class functionality for the same function exactly similar to this. I will say super dot whatever is the name of task and function, then I will implement my additional functionality. So that is where this super keyword becomes very useful, and this concept that we have a base class, we are extending, and then we are overriding the methods of the base class to extend its functionality. See, we are saying we are extending functionality. When we say we are extending functionality, it can be done in two ways. One is I add new functionality, right? So how do I add new functionality? I can declare new properties, or I can add new methods. So that is one way I can extend the functionality. And the second way I extend the functionality is by adding the functionality to the existing tasks or functions. And when I do that, I need to call the base functionality, then plus I need to do something extra. So when I want to do that, I will say super dot call the base functionality, and then I will add something extra. So that is how I am extending the functionality. I am reusing it, and I am extending the functionality by adding new, and by extending by adding to the existing tasks and functionalities as well. So both the ways you can extend the functionality using the inheritance. And one thing we need to note is that if you have multiple levels of inheritance, you can't just say super dot and look through all the hierarchies. This is not how it works. This is not legal. Okay, so even if you have multiple levels of inheritance, it has to be chained, right? So like here, the way I'm calling super dot new, if the base test was extended from another base class, and then the constructor of the base test should have called super dot new. So that way it goes step by step, gets linked chained to the base class. But you can't from the inherited class, you can't traverse multiple level up. You can traverse only one level up, and from that this guy can travel one level up using the super keyword. So that's how it works. Okay, so when we start this concept of inheritance, right? So we are able to, like, there's a derived class and a base class. And when we have already been seeing that when the derived class extends the base class, everything that is present within the base class becomes accessible to the derived class. Okay, and we achieve it through the extend keyword. Now, there are cases where you don't want everything to become accessible, or you want only the derived class to access some of the properties that are present, properties or methods that are present within the base class, but you don't want it to be accessible outside. Outside meaning, if I created a derived class handle and an outside world wants to access a derived class object handle dot a base class property or a method, you don't want that to be accessible to the outside world, but you only want, like within the derived class, you want it to be accessible. So when I did extend and I'm writing a function or a method within the extended class, I should be able to access the properties or methods that are declared in the base class, but I don't want them to be accessible when the derived class handle is created. Then you need to rely on the concepts of data hiding and encapsulation. So pay attention to the terms as well. But before we go into it, anything unqualified, that is without any qualifiers. So we're going to talk about what are the qualifiers. All the class properties and methods are public. Okay, so public meaning anybody who extends will be able to access it, and anybody who creates an object of that particular type can access it using the dot notation. So he can say object dot property name or object dot method name, he will be able to access it, and anybody who has extended it will be able to access it as if it belongs to them using the keyword this dot something, this dot property name or this dot method are accessible. So it's all public by default. So if you want to prevent that usage, okay, there are two ways. So this is the concept of data hiding and data encapsulation. So you can add these two qualifiers before you declare the variable names. Okay, so we look at it how you can do that. So but for now let's understand the definition of it. So this is local. So what happens is when you do it as a local, that particular method or the property becomes only accessible inside that particular class. Okay, and this cannot be then these methods and these properties will neither be accessible to a derived class, nor it will be accessible through the object. Okay, in both the ways it won't be accessible. The derived class cannot see it, and through the object handle dot notation we cannot access it. And there is another qualifier called protected. So when you use the protected, this concept is also called as data encapsulation. So when you use the protected keyword, what happens is that particular class property or method has all the characteristics of your local member, except that it can be inherited. Okay, it can be inherited means it will be visible within the subclass. But again, even if I create an object of the type subclass, if I try to do object dot that particular property or a method that is local, that is a protected in the base class, I will not be able to access it outside, but I can use this dot and I can access those protected base class properties and methods. And why we do this type of protection is because what happens, sometimes we might have some internal variables within the base class which we are modifying to create some other state, and we don't want somebody to look at it. Okay, so you might ask question, why do you not want somebody to look at it? So what happens, today I might have an internal variable that I might be using as an up counter, right? Now tomorrow I might be able to achieve the same functionality using it as a down counter, right? I mean, I can do that, right? Like I can create an internal variable, call it as count, and I can count up to 10. I can initialize the same variable to 10 and decrement it to 0 and accomplish the same functionality. But if somebody relies on that variable to do something, initially he will think I'll be incrementing that particular variable, and then eventually I want to change my implementation to decrementing implementation, and then the derived class would get confused. So what I want them to see the effect of it, right, and not how I am going to accomplish it. So in those cases, what you can do is you can declare them as local and make the effect accessible through the public functions, okay, and or any other public properties, but whatever that you intend to use it for your own modifications, so that you retain the freedom of that particular class to change it and not affect the other class that is using that particular functionality. So that is a area in which you want to use the concepts of local and protected. So these concepts are also used quite heavily in the UVM as well. So a lot of UVM's own implementation is either made local if only that particular class accesses it, or made protected so that only its corresponding hierarchy can access it. So these concepts are very predominantly used in the UVM. Even when you implement, you have to make sure to restrict the interface to the class such that we promote the concept of low coupling. So keeping the inheritance context in mind, we have two ways to access variables. One, the inherited class trying to access its base class properties and methods, and second is when the objects are created using the dot notation, object dot whatever the property or name. There are two ways to access them, and now through this example, let's understand how the local and protected behave in both of those contexts. Okay, so now here I have a class, let's say IP. It's an interrupt handler, it's IP level interrupt handler, and it's simply implementing some mask, and that's qualified through this local qualifier. So you say local data type name and the variable name, so it has to be prefixed before your data type, and then I'm saying protected, again the data type and the name of the variable, right? So these are the two variables that I've declared in the IP interrupt handler, and then in my constructor I'm taking some mask, then internal mask, I'm doing some operation and storing it, SOC mask, and again I'm doing some operation between the mask and the internal mask, and I'm storing an SOC mask. I have iDisplay function where I'm trying to display both the local as well as the protected values through the base function, the base class. Okay, so now this IP handler, now I reuse this IP handler at SOC. Typically you do that. Okay, you build some functionality at IP level, and when you want to take the same functionality at the SOC level, you extend it. That is a natural way. Now you accomplish reuse. This type of reuse is called vertical reuse. So you are going from IP to subsystem to SOC. So there's a vertical reuse that you're trying to do, and there can be horizontal reuse. Therein you have something that you have built for PCIe IP, you want to use it for USB IP, so that's a horizontal reuse. So the peer hierarchy level is trying to reuse some functionality, it's a horizontal reuse, and in this case we are going the vertical reuse. So we are saying class SOC interrupt handler extends the IP handler. So IP functionality we are trying to reuse it at SOC level. We are overriding the constructor, we are calling super.new because we have an argument. As we have already seen, the implicit constructor won't work here. I am also overriding this iDisplay function, and I am doing exactly same thing. I am displaying internal mask and the SOC mask. So now, as we have seen, there are two ways to access these variables that I have declared it in the base class. One is within the derived class, and another one is using the object and the dot notation. Okay, so first let's look at it in the derived class. So when I do this internal mask and internal mask, okay, so this is illegal. Okay, why is it illegal? Because this internal mask is local to IP handler. This is IP's own way of doing things. Okay, the SOC doesn't need to know about it. Okay, it's some internal stuff, right? So when you try to access the local variable of the base class in the derived class, it is illegal. It's going to give you the error. But if you access a SOC mask, then it is legal because it's a protected, and the protected variables can be accessed in the derived class, or in the subsequent subclasses also SOC mask can be accessed. Okay, that's your data encapsulation. Okay, but if I now so this is one factor. Now let's look at this one way of accessing, and we understand what is legal and what is illegal. In the second way, where we use the object and dot notation, so I am now creating one IP handler object over here and one SOC interrupt handler object over here by calling new and passing some argument value. And when I say now the base class handle dot internal mask, okay, I am using the base class. Okay, base class handle dot internal mask, I already have created an object. This will be illegal. Why is it illegal? Because it is local. Local meaning that it can be only used within the class. Even with the object dot notation, it is not accessible. And if I try to access SOC mask, which is a protected, it is also a error. It is illegal because protected variables can only be accessed within the your derived class, not using the dot notation. Now if I take a derived class handle and try to access the internal mask, so in the derived class, even when we try to access a local variable, it was error. Even with the derived class object handle, when we try to access the internal mask, it is still error. Okay, and with the derived class handle, if I try to access the protected variable with the dot notation, it is still error. But I can use it within the class. Okay, the protected variable can be used in the subclasses but cannot be used with the outside world by using the object and the dot notation. It is illegal. But I can call a function that a base class provides, and that function can access both the local and protected members. Okay, but I cannot access them directly. Okay, so these are the ways in which you control the visibility into the object. So this is the way anybody uses the object, correct? So when somebody uses the object like this, then you control the visibility into those objects using the local and protected keywords. So I hope this concept is clear. Okay, so in the previous slide we saw how we can have a base class and we can extend the functionality of it by adding new functionality or by overriding the existing methods in the base class and then calling the base class method using the super and then adding on to the functionality that is present in the derived class. So we saw that mode of reuse in the context of inheritance. Now we look at inheritance from a different angle, and this angle is we start preparing ourselves to move to the concept of polymorphism. Okay, so in this case what we are going to do is we want to override the functionality of a base class and change it altogether. We want to implement a new functionality in the derived class and we don't want to use the base class functionality. That also is a valid use case. So how do we do that? We'll look into it. So here first let's understand a quick example. So I have a class packet, I have a property integer I equal to 1, I have a method function, return type is integer get, and get is the name of the function is the name of the internal variable that gets created, and then we are saying get equal to I, and function, whoever calls the function get, I will return the value of I. Very simple. Next, I have a class linked packet which is extending, which is inheriting the packet, and then I'm overriding the property itself. I'm saying integer I equal to the value, I've changed it to 2. I'm overriding this particular method function, so I'm saying function integer get, and then the prototype is always same, function declaration is same. I'm saying get equal to minus of I, so I'm just changing slightly and I'm ending the class. So I have now the extended or the derived class. So now what is in this whole thing? Okay, now this subclass or a derived class object. Okay, so now let's say if I said linked packet data type. So class is a data type. So I say linked packet. I declared a handle LP and I did equal to new, wherein I created an object of the type linked packet. Okay, so now at this point, before we jump into the next of the code, let's come back to the concepts. So what we want to say that we have now an object of the type linked packet. What we want to say is also a legal representative object of their base class. A subclass or a derived class objects are also legal representative objects of their base class. Okay, so what that means is that if I have an object of the type link packet type, which is a derived class type of an object, is also a legal representative of its base class object, that is a packet. Okay, so now if it is a legal representative, then what it means is that I should be able to access the base class properties through the linked or the derived class object, right? That is possible, right? Because I am saying it is a legal representative for that. So let's see whether that happens. So now what I do is I create one base class handle packet data type, which is a base class data type, and P. And what I do is I assign the handle of the derived class to this base class, and I had already created an object of the derived class. So now the derived class object is being pointed by a base class. Okay, so and I am saying it can be a legal representative. So now what I'm going to say, if I say j equal to p of I, now my p is pointing to a derived class object. So what is the value of the I that I'm going to get, right? So is it I'm going to get the derived class value or am I going to get the base class value? So here you will get a base class value. So the j will become equal to 1, which is the value that we had seen in the base class, not the one that we had seen in the derived class. Okay, so what this means is when the handle of linked packet is assigned to a packet variable, that is in the line 53 we have assigned it, then the base class handle, right? So since now p is a base class handle, all the overridden members of linked packet now gets hidden. It just becomes a base class object. Okay, so like we are not able to see I equal to 2. Same thing if I call p.get, okay, I am going to get j equal to 1, not -1 or not -2. Okay, this, forget about this, whatever the block is not going to get -1 or -2, it's going to get 1. Okay, so when we call the overridden methods, okay, through a derived class, which is derived class object that is assigned to a base class, we will still be calling the base class functions and base class methods. Okay, so the derived class functionality gets hidden. But if I had created the linked packet and if I call lp.I over here, then I would have gotten 2. Okay, so that is possible. And if I call lp.get, I am going to get -2. So the functionality is overridden. Okay, but if I access a derived object with the base class handle, this is a very important point. Okay, with the base class handle, then even the derived object will behave as a representative of its base class object, and which will allow you access to the base class methods and the base class properties, and not the derived class methods or properties. Now if you wanted to call the overridden method via base class object handle, okay, and then what we need is we need the method to be declared as virtual. Okay, so what is this virtual? We will find out in the next slide. Okay, so we will look at more details of virtual keyword and its usage in the context of polymorphism. Here we are going to only briefly touch base upon that. Okay, so I want to give you guys the alert that this slide is going to be a slightly tricky slide. Okay, it's a tricky concept. So just pay attention. What we are trying to do over here is that we already saw that when we have a derived class, okay, and we have a derived class object, and when we assign that derived class object to a base class handle, how it behaves we already saw. Okay, so when we assigned it, we know that every derived class is also a legal representative for its base class object. And when we assign a derived class object to a base class handle, and when we try to access the overridden properties and methods of derived class through a base class handle, its derived nature got hidden. Okay, that is a point up to which we have looked at it. Now that assignment is a legal assignment. So as we saw already, that we can assign a derived class handle to a base class handle directly, and it's a legal. Okay, but when if I do other way around, that is I created a base class handle and I created a base class object, and if I assign it to a derived class handle, then it is going to result in a compile error. Okay, so that it results in a compile error. I'm going this direction, it will result in a compile error. Now one question might come in your mind that why does it result in a compile error? Okay, so now imagine this, right? So I have a base class in which I have declared one int variable, and I have extended that class, and in the extended class I have added two more int variables. So now when I create a handle of a derived class, I need to allocate storage for three int variables. Whereas when I create a base class object, I need to allocate storage for only one int variable. So when you have created an object which has a capacity to store only one int variable, you cannot assign it to a derived class object handle which requires a capacity to store three int properties, right? So that is why it's an error. So it will give a compile error. Whereas you can do $cast if you really want to assign a base class handle to a derived class handle. Okay, and please note that this is the confusing concept. So now we already know it's not doesn't have the storage, so we are not able to assign. So how does $cast is going to solve? Okay, so $cast is not going to solve it. So what happens is, in the object oriented programming, this is one key concept that I want you guys to understand, that you can create and define a base class, and then many people can extend that particular base class and implement many derived classes out of it. But when the communication happens between two classes, wherein you might still have to, so in the base implementation I'm talking about, so our base implementation, then somebody is taking that base implementation and doing additional enhancement. But within the base implementation, when you are passing an object of one form to another component, you are going to be passing a base class object. Okay, but when the functionality gets enhanced, you want to be able to pass the derived class object handles, but the code to pass those handles is already written. Okay, so and in those definitions, we are already using a base class handles, and through those base class handles we now want to send a derived class object because that is legal. But at the destination, when we receive it, we still want to treat the object coming in as a derived class object. Okay, that is possible because it's just traversing through the base class handle, and in order to do that we need to use the $cast. Okay, $cast will check whether a base class object handle is holding an object of the type derived class, and if it is holding an object of derived class, then you can use it as a derived class. Okay, that is what is a $cast. It's not that the base class object is becoming a derived class. No, that is not what is happening. It is a base class handle that is carrying an object of a derived class is being treated as a derived class object handle. That is what is happening when you do the $cast. And let's look at with an example. So let's say I'm just simplifying UVM over here. Don't worry too much about the UVM detail. So I have an UVM object, and that UVM object will have this function called virtual function void do copy. Okay, and it's using the virtual keyword, and what I want is that this is actually implementing a deep copy functionality. So we had seen in the previous case when we were assigning the class handles, we had pointer copy, shallow copy, and deep copy. So here we are going to be look at how do you implement a deep copy function. One of the ways to implement deep copy function. So UVM object provides an virtual function, and our class packet is extending that particular object, and it's overriding this function called do copy. And since it is virtual, when I call my function, okay, even if I call it with a base class object, it is going to get invoked. Just keep that point in mind. Not that we are worried about that point at this point. Since this keyword is there, I am briefly mentioning about it. We will come to it when we go to the polymorphism. So we have written this do copy function, and the way it gets used is something like this. So I have declared a packet P1 and P2, two handles, and I am declaring two objects. Let's say I randomize the object P2. I'm not showing it over here due to the lack of space, but let's say I randomize object P2, and then what I want to do is I want to copy the P2 to P1. So I'll call P1.copy P2. So when I say copy in the UVM, it is automatically going to invoke do copy. Just take that on the face value. So when that invokes the do copy, what we are trying to do over here is where you need to pay attention. So here what I am doing is this is the deep copy function that I am implementing for the object of the type packet. So I am declaring one handle of the type packet underscore packet. But if you see here, we are still, because this function declaration was provided in the base class, the object handle is of the type base class. So it's still a UVM object. I am saying RHS, but if you see what I am passing it as an argument, I am passing an argument of a derived class. Okay, so a derived class object, that object that I had created over here, is traversing through a base class handle RHS. It is traveling through that. Now before I can copy, so now my RHS will have all the fields, like let's say I have declared M address, right, in my derived class. This is an additional field that I have declared. That field is present because the storage is allocated, right? I have done the P2 equal to new, so the storage has been allocated. I want to access it, but it is coming via a base class handle. So what do I need to do? I need to first check whether this base class object handle, does it really contain a object of the type packet. So what I have done, I have declared one handle of the type packet, okay, and I am checking with a $cast. So when I do this $cast, and what it is saying is, can this object which is present in the handle RHS, is it assignment compatible to this packet type? That's what it's going to check. Since both are of the same type, since I'm passing the packet type, the $cast is going to succeed, right? And since the $cast, of course, we need to check over here, and we should check if $cast, and then only we need to do the assignments. So the $cast is going to succeed, and then what I'm going to do, I am going to copy my M address from the packet transaction packet object into my current M address, right? So that is what I am doing it over here. And if I had any objects inside this, I need to invoke the copy functionality for those objects as well to chain the deep copy from happening. Okay, so that is what I am doing. So what we are doing over here is, when the $cast has succeeded, it's just that we have ensured that the base class contained a derived class object. Okay, and this is the concept that gets heavily used in the UVM, and this is the deep copy example that I have shown over here. I know this concept is little tricky, so you might have to look at it couple of times to get it, but the fundamental point is that a derived class object was traversing through a base class handle, and only when that is happening we can do a dollar cast and check it, and if that matches then we can access it as a derived class. So this is the main idea of casting.